Welcome aboard the System76 transmission log. Our broadcast is about to begin. This is the latest on System76 computers, manufacturing, and Pop! OS. Now for your in-orbit crew.
Thanks for joining us today. I'm Emma, and I'm here with David from production, and we're excited for today's episode. We have some great company announcements and a really cool guest who'll be talking about astronomy and his research on nebula space clusters. We have our back-to-school sale going strong until October 3rd, where you can get up to $150 off computers, and swag giveaways will happen throughout.
Emma, are there any other community things that happened last month that you want to announce?
Well, as of this recording, we have our first monthly POP meetup this week, which is exciting. We're going to be meeting at unique locations every month to enjoy delicious food and drinks and great conversations. So I can't wait to make all the new friends.
We are also hiring a mechanical engineer and a production technician. Both jobs are listed on our careers page. That production technician position is actually my position because I will be leaving soon. So if you want to come and take my job, please come and do that. It is a great company to work for.
That's awesome, but we'll miss you. Wonder what's new in Cosmic? A lot. We'll start with our tiling and mouse updates. We have some stacking updates. The notifications are now existing in their own applet, separate from your calendar. So multiple notifications from the same applications will stack in the notification center, reducing clutter. OKLCH color encoder was implemented for custom theming, and the Polkit system-wide permissions handling will now prompt a password for special access or changes. Also, there are some X-Wayland fixes to drop-downs and pop-ups for X apps in Wayland.
The Ryzen 9 7900X3D with AMD 3D V-Cache is now available on Thelio Major. Recent gaming news has been about how it's beating Intel in performance for gaming, so that's exciting.
All right, and that's the news.
Our interview this month is with Massimo Pascale and his research work in globular clusters, which we thought was fitting with the excitement of the Nebula product launch.
Why don't you start by telling us a little bit about yourself?
Yeah, definitely. So I'm Massimo Pascale. I'm a fifth-year graduate student at UC Berkeley Astronomy. I did my undergrad at the University of Arizona in Tucson and graduated in 2019, after which I came over here to start my graduate studies in astrophysics. And so I've been doing that now for 5 years and still loving every bit of it.
So you're studying astrophysics at Berkeley. What is something within astrophysics that you're particularly interested in?
Right now, my particular interest in astrophysics is really how clusters of stars evolve and how our observation of that can be aided through gravitational lensing, which is all stuff that I can get into a little bit later. But something that I find that's really beautiful about astrophysics is that once you gain a context for any individual thing within it, you gain an appreciation for it. I think most things can become very interesting. So I guess that's a long-winded way of saying that this is what I'm interested in right now, but should I decide to move in another direction, I'm sure that there are many other things that I would be interested in and will be interested in the future.
In our last conversation with you, you mentioned that you're studying early galaxies and dark matter in the Sunburst Arc. What is the Sunburst Arc and why that particular arc?
Right. So before we get into what the Sunburst Arc is in particular, I think it's important to explain what gravitational lensing is and the context in which we're viewing gravitational lensing. And so Einstein, more than 100 years ago, predicted that objects that have mass or energy deform space-time. So we all kind of exist on this space-time and our mass deforms it. And when light actually travels along those deformed paths. And that's what we end up observing as the gravitational effect. So this is not just light, but it's really every object. Let's say a comet is flying by the Earth. The gravitational pull of the Earth is actually going to deflect the path of that comet, right? And what's very interesting and what Einstein predicted is that light does the exact same thing. And so we're replacing the massive body, which in this case I had said was the Earth, with instead a massive galaxy cluster. Take the mass of our sun and you multiply it by 10 to the 15. That's what you get as that mass for the galaxy cluster. So extremely, extremely massive. And so that's situated far out from us in space. Situated behind that galaxy cluster is then even further away a individual galaxy. And when something's very far away, we usually refer to it in astronomy as being high redshift. And so that very distant high redshift galaxy, the light from it, you imagine it'd be so far away that usually it would be difficult to see because that light, the intensity falls off as it's further away and it becomes fainter. But when it's situated behind that massive galaxy cluster, as I mentioned, the gravity from that massive galaxy cluster ends up deforming spacetime and changing the path of light. And what's very interesting about the distortion is that it provides a magnifying effect. So we actually see it brighter than we would otherwise. And so that's something that I find that's very cool, is that these massive galaxy clusters actually serve as natural telescopes in the sky that allow us to see galaxies that are much further behind them. And we can see things a lot brighter than we would be able to otherwise.
So that's gravitational lensing? Cool.
Yeah. And so there's a lot of reasons why this is an arc of great interest. I think it used to be the brightest known arc on the sky. And so because it was exceptionally bright, that means that you can get very high quality data. Astronomy, particularly observational astronomy, we're always fighting with the noise in all of our data, right? We're trying to find signal amongst noise, and the brighter things have more signal. And so we're able to pick out more above all of that noise. And so when we last talked, I was interested in how the sunburst arc could be affected by small scale dark matter, this matter that doesn't interact with light whatsoever, but its gravitational effects are still measurable, which is why it still impacts this gravitational lensing. And so the distortion that we see in the sunburst arc and the magnifying effect that we get is due to all of that matter, whether it be visible or dark. And so in the past, we were looking at this arc and we were trying to look at how smaller scale changes in the dark matter could affect what we end up seeing in the arc. But more recently, we've actually shifted our focus. So we spent so much time studying the sunburst arc from the perspective of, okay, what was doing the lensing, to now looking at the sunburst arc and thinking, oh, the thing that's being lensed is actually very interesting as well. These massive, very young star clusters, almost harkening back to what I said before about my interest in astrophysics can change because once you get an appreciation for a different type of problem, I think most things in astrophysics can be found very interesting.
That's really cool. Can you tell us more about superstar clusters? And when you say they are rare, what does that mean in this context?
So let's back up to the scope of the problem and talk about specifically why I'm interested in the sunburst arc, which I alluded to before. And so in the sunburst arc, we have an individual galaxy, and the galaxy has been stretched out into this arc-like shape. When it gets all stretched out, we get to see these finer details in the morphology of the galaxy that we didn't get to before. And so when you actually look at images of the sunburst arc, I highly encourage you to Google the sunburst arc and take a look at a picture. It's very pretty. You see all of these bright knots, these sort of bright little compact circles within the sunburst arc. And so when you look at those with your telescope, and in particular, when you look at it with a spectrograph, so it kind of splits up all of the light into its different wavelengths, you notice that it has features that resemble a very young, very massive star cluster. We refer to these as superstar clusters. And so why do we even care about superstar clusters? Well, first of all, getting the most massive superstar clusters, so we're talking, order 10 to the 6 solar masses, is pretty difficult to do in our local universe. So, ideally, if we could, we would observe everything in the local universe because everything's very close by. And that makes the data that we're able to get very, very high quality, right? Because it's closer and so everything's brighter and we get higher signal to noise. But we find that in the local universe, so at low redshift or very close to us, it's very difficult to find these superstar clusters. Whereas when we seem to go very far away to the high redshift universe, we seem to see more. So when I say that we're looking at something at high redshift, really what I'm saying is that we're looking at an object in the universe as it was when the universe was younger. We're really looking billions of years into the past, where the universe was a different place. It was a bit of a different environment. And so because of that difference in environment, it's maybe more conducive towards discovering superstar clusters of the high redshift universe. So that's one reason why we might be interested in looking at the sunburst arc, is because it hosts the superstar cluster, and the superstar clusters tend to be difficult to find in the local universe. But now let's go even one step further back and say, okay, well, why should we be interested in these superstar clusters as a whole, right? If I tell you that they're rare, that doesn't really necessarily mean that they're interesting. There can be rare things that are not worth exploring. And so these tie into a different type of star cluster that we refer to as globular clusters. And so globular clusters are some of the most outstanding objects in astrophysics.
Before we move on to the next question, I just wanted to say that I did Google the Sunburst Arc, and that is very fascinating to look at. And I could not stop looking at it for a good few minutes while listening. It is, I highly encourage anybody listening to definitely Google a Sunburst Arc and take a good look at it.
Right. Yeah, it's very cool. And because it's stretched out, it's distorted. It's not what you expect when you look at space, right? You don't expect to see some really long looking thing. But yeah, it's very, very cool.
I honestly probably wouldn't have given it much of a second thought without your explanation.
Thank you.
So I think you were about to tell us more about globular clusters.
Right. So when we look in the local universe, we see these very compact clusters of stars, and they're usually quite massive. And for a long time, people thought that these were what we call a simple stellar population, meaning that they probably all formed out of the same gas cloud. And so that's how all these stars form, right? You have some gas cloud, eventually it collapses. And as that gas collapses and gets more and more dense, eventually it starts to form stars. And so in the simplest picture, you'd imagine that there's some cloud sitting out in space. At one point it collapses and forms a whole bunch of stars that are then all together in a cluster. And so when we look at globular clusters, we initially thought that this was what was going on. In particular, we're seeing it really late in the stage of its evolution. So all of these globular clusters we see are billions of years old. And so that's one reason why people are so interested in them, is because they're billions of years old, that means that they formed when the universe was very young. And so people can sort of do an archaeology by looking at these globular clusters to get an understanding of, okay, if we understand how these form, then we might have a general idea of how stars are forming generally in the early universe, right? Because they're billions and billions of years old. And so these superstar clusters are sort of thought to be the progenitors or eventually evolve into these globular clusters. And so that's what's interesting about the Sunburst Arc, is that maybe we're looking at something that will one day become these old globular clusters that we see in the local universe or nearby today. And so this is all going to sort of connect into what's called the multiple populations problem. So I had mentioned before that when we looked at these globular clusters, we kind of imagined them to be simple stellar populations. And by that, I meant that, the whole cluster probably formed out of the same cloud. And so the cloud, let's imagine the cloud that it formed out of, has some characteristic, what we call metallicity, which means how much metals does it have relative to hydrogen. And another way of saying that is, what's the chemical makeup, right? So we know that the periodic table of elements, typically most things are composed of mostly hydrogen, but there are all of these other elements that we're familiar with, things like carbon and sodium and nitrogen, et cetera. And so you imagine that the cloud is probably some mixture of all of these elements, and that it's probably well mixed throughout, right? So it's fairly homogeneous. No matter where I look at the cloud, I probably see the same distribution of hydrogen and nitrogen and carbon and so on. And so when that cloud collapses to form stars, I'd imagine that all of those stars would have that exact same chemical makeup, right? And so we can actually do this. We can go and we can look at the stars in these globular clusters and we can say, okay, what's the chemical makeup of these stars? If we were operating under that assumption that it was some simple stellar population, that it just all formed out of the same cloud, then we would expect to look at every star and say, okay, it has the exact same chemical makeup. What's particularly interesting is that when we look at these stars, we actually end up seeing populations that fall into broadly two categories, depending on their chemical makeup. And so one has a chemical makeup that's very expected. If you look at other stars in the field, so ones that aren't in clusters, they seem to have similar chemical makeups to what you would expect in this population. We call this the 1P population. Then there's a secondary population that exhibits this weird correlation and anti-correlation between certain elements. That being something like nitrogen, we see that nitrogen and sodium are enhanced in these stars, while things like carbon and neon seem to be more deficient in these stars compared to what we would expect or what we at least see in this 1P population. And so we call this one that exhibits the weird correlations and anti-correlations the 2P population. And so I know that doesn't seem like a big deal. You're like, okay, so what? There's some extra nitrogen in some of these stars. But we can't come up with a good explanation for really what's going on, right? And so that comes to the root of really astrophysics, is that if we don't understand what's going on and nobody can seem to figure it out, then suddenly it becomes a very big problem. And so this problem's been known for decades at this point. We've made some progress, but we haven't quite gotten there. You might ask, okay, well, what if we could see these clusters as if they were back in time? Maybe we would catch the processes in action that might be causing this weird correlation we see between some of the elements in the 2P population. And so that's where these superstar clusters once again come into play. I mentioned that, a superstar cluster is thought to be the thing that will eventually evolve into a globular cluster. And so if we look at these superstar clusters when they're young, maybe we can see the processes in action that could lead to the multiple populations problem. In particular, when we looked at the Sunburst Arc, which is a superstar cluster, we found that the nebula that surrounds it, so the remaining gas that surrounds it, was significantly enriched in nitrogen. And this is similar to what we see in those 2P stars. In those 2P stars, we see that nitrogen is enhanced relative to what we'd expect. And so when we go and we look at the younger version, maybe, of this cluster, we see that the gas that is surrounding it, which may still be able to form stars, right? That remaining gas may form another generation of stars, seems to be nitrogen enriched, sort of cluing us in like, okay, well, maybe we're seeing a progenitor of a globular cluster here, and we're seeing the clouds that will eventually become that 2P population.
What does the nitrogen enriched mean or cause?
Right. So I think now we're going to get a little bit more into the weeds, but I think it's a key thing to understand the multiple populations problem. First, what we have to do is we have to understand how stars work. And so stars work by doing what we call fusing hydrogen into helium. You might have heard a lot about, in day-to-day science about how on Earth we're trying to be able to do fusion. That's what stars do naturally, but they're able to do it because they have so much mass, right? More than we could ever build up on Earth. They're fusing hydrogen into helium, and that's what causes stars to sort of stay active. That fusion of hydrogen into helium allows the star to not collapse, and it's what provides all of that light that we see from the star and all of that energy. And so there are a number of different ways in which that can happen. There's sort of the very base way to do it, but as you get to higher temperatures, so the star is very hot, as you get the star hotter and hotter, it actually opens up new pathways for you to fuse hydrogen into helium. In particular, one that's called the carbon, nitrogen, oxygen cycle. So now we're getting very deep in, but just bear with me here. These carbon, nitrogen, and oxygen, they actually serve as a catalyst for this conversion of hydrogen into helium, but it only becomes activated at higher temperatures. But because they serve as catalysts, as soon as you can access it, as soon as you are at those temperatures, it's going to quickly become the most preferred way to do it. And when you do that, it causes certain imbalances between the initial makeup that you had of the star with respect to carbon, nitrogen, and oxygen. And so what people think is that maybe these very high temperature stars that are undergoing this carbon, nitrogen, oxygen cycle could be causing the enrichment of nitrogen that we see. But you still need a way to get that material out of the star. And so there are a lot of different ways. We call this stellar winds. And I won't get into the details, but the most massive stars, which are also the highest temperature stars, and hence the ones that are undergoing the CNO cycle, tend to spew out a lot of their mass in the form of winds. They're so bright, there's so much energy that it starts expelling out its own material. And that material can eventually get captured by gas clouds that maybe surround the star. And so when we're thinking about, okay, well, what could be causing the enrichment that we see of nitrogen in this nebula that surrounds the Sunburst Arc, right? So there's this massive superstar cluster, and there's this cloud that surrounds it. And we looked at, basically what we did is we looked at the features of the cloud, and we found that the cloud had elevated nitrogen compared to what we would expect. And so maybe it's these very massive, very high temperature stars that are undergoing the carbon, nitrogen, oxygen cycle that are spewing out material from them that might be enriched in nitrogen, and that's getting captured by those surrounding clouds. You could even take that a step further, and you could say, okay, well, now we have some gas clouds that have been enriched in nitrogen. What if those clouds end up collapsing and forming stars themselves, right? Because that's how stars form. And so, maybe in the Sunburst Arc, we could be seeing that 2P population still in its nebular form. where the enrichment has been caused by ejected material from the most massive, highest temperature stars.
What are some things you wish people knew about space?
I think that when we think about the general public and the relationship with astronomy and space in general, people definitely have an appreciation for how big space is and how, sometimes unfathomably intricate space can be, right? So there's this great unknown out there and all of these other stars and planets and giant clouds of gas and what have you. And I think that is really great because it gives everybody sort of a sense of perspective. I think when you learn about the vastness of the universe, sometimes it can make you feel small, and that can be a good thing. I think it can really change how you see day-to-day life. Indeed, Neil deGrasse Tyson has a great talk about how once we went to the moon, it gave people a greater sense of understanding of the scale of the universe and where we were within it, and how that changed people's relationship with the Earth and really stuff like climate change and such. And so I think that's all really, really great. But I think that's something that people already understand, even if maybe they can't put their finger on it. I think it's something that they already kind of know. But from an astrophysicist perspective, I think that something that's very cool is that in the face of a universe that is so vast, so complicated, so difficult to understand, that really if we take things one step at a time, we take things one problem at a time, one calculation at a time, slowly but surely we can really build up a very intricate picture of what's going on. The depth of knowledge we have about very detailed things in space is really sometimes very mind-blowing. And I think goes to show just how much we've been able to accomplish in the past, say 100, 200 years of really doing in-depth study of physics and astronomy. I think that that's something that I'd like people to keep in mind more. I think people are very fascinated by the mystery of space. And that's great because space is mysterious and that's very cool and it gets people excited. But also to get an appreciation for how much progress we've been able to make and will continue to make into understanding really this beast of a universe that we have.
How do you see the future of astronomy evolving with the integration of computational techniques, advanced telescopes, and collaborative efforts among researchers?
I think that it's a difficult question to answer. Really, we're at a stage where astronomy is sometimes moving faster than you can keep up with. There are a lot of people that indeed are able to make their careers off of just really staying on top of the advancements in things like computational techniques, or becoming acquainted with the most recent telescopes. But sort of going down the list, I'd say, so computational techniques, especially the sort of now as we're entering in an era where machine learning is becoming more and more accessible, we're finding more and more ways to apply that to the problems of interest. I expect that that's going to continue to sort of push the problems that we have access to. So there are a lot of problems that are sort of locked behind closed doors in terms of computation time. They just take too long, especially problems that have lots of data. So this is also now combining into advanced telescopes. So we're now coming out with these telescopes that can take incredible amounts of data, sort of pushing towards this more survey approach where you take lots and lots of data at once of many different objects. A great example of this would be the Vera Rubin Observatory, which will go up in the next few years. We're starting to, at one point, have too much data compared to the number of people that can work on it. And so whoever can sort of harness computational techniques to be able to go through very large amounts of data in a reasonable amount of time and extract the important information from it really stands to benefit a lot from the current era of astronomy. And so I think this also goes hand in hand with collaborative efforts, because each of these telescopes really is a massive collaborative effort, right? So you might hear of the James Webb Space Telescope that went up. Of course, that was a huge collaboration across people really around the world and governments around the world. And I think was like a crowning achievement really for it's like an achievement for humanity as a whole. We're in an era now where collaboration between researchers is sort of more accessible than ever, especially now that people are more comfortable being online and interacting through things like Zoom. I think that we're going to see even more collaboration going forward. And that's great, because I think maybe many people, when they think about astronomers or physicists, they kind of get the idea of somebody that's, in their office on the chalkboard solving problems on their own. But the reality is that we actually all collaborate a lot. And that's really fun. I think part of the most enjoyable experience of astronomy and having success in this field or attacking certain problems is being able to do it together with other people. I think that more and more collaboration is always a good thing. I think it's on the rise because, now people are so connected. And at the end of the day, I just really love collaborating. I think it's super fun to be able to do things with other people.
It sounds like it's a good community to be a part of.
Yeah, definitely. I think any community can have its ups and downs, but I think we're all sort of together trying to solve the same problems. And there's a mutual respect from that.
That's awesome. So I know that you had selected a Lemur Pro previously. What did you take into account when it came to your studies, and why did you select a Lemur Pro?
When I was thinking about it, I kind of wanted the most power that I could get in the smallest footprint. So I guess the highest density of power in a laptop. And so the Lemur Pro seemed to check all of those boxes. I didn't really need to go up to the next stage where I needed, maybe some dedicated graphics. There definitely are astrophysicists that make very good use of those, but that wasn't me in particular. So the Lemur Pro allowed me to have a lot of power, a lot of RAM for what I needed to do. And it was small enough that I felt very comfortable taking it with me everywhere. So in astronomy, I'm either going to and from campus, and maybe that's difficult, or maybe I'm going to a coffee shop, and so I want to make sure to have a small footprint. But also, one of the big benefits and one of the most important parts about our field is that whenever we have a discovery, you need to be able to share that discovery. And so usually we do that by publishing papers, right? And then we put the paper out on the archive or some journal publishes that paper. But there's so many papers coming out every day, it's very difficult to keep track of everything that's going on. And even if you have a very cool paper, it can end up getting lost in the sea of other works that are coming out day to day. Often we'll go to conferences where we will go and present our papers. And so we hold an entire room of other astronomers captive as we get to talk about our work for 15 minutes, upwards of an hour, depending on what the conference is. When I'm thinking about what device that I want with me, I want one that I feel very comfortable traveling with to other states or to other countries and being able to take out in a conference setting. I don't really want to lug out a giant gaming computer when I'm sitting in a room of 100 other astronomers and somebody's trying to give a talk. And so those were the main things that factored into my Lemur Pro decision. And I think that my intuition was right because I really enjoy the size of it. And I never feel myself yearning for any more power in the computer, particularly having I think there's 40 gigabytes of RAM in the Lemur Pro that I have. And that's very, very useful because it means I can have a lot of different projects open simultaneously. I don't have to start closing out of things and start from a clean slate. I'm really loving the Lemur Pro and it really checks all the boxes that I have.
Can you talk about the relationship between open source and astronomy?
In astronomy, everything for the most part is open source to some extent. And the reason being is that the most important, or really the foundation of science, is reproducibility. So if I come out and, let's say I have some big discovery and people say, okay, well, how did you get this big discovery? I'll say, maybe I wrote some giant software that does some big simulation, right? But if they go, okay, well, show us the simulation. And I say, no, you can't see that. This code belongs to me. You can't see what's going on under the hood. Nobody's going to believe what my results are, right? If they can't go in and actually see all of the little intricate details of what's going on and more so be able to reproduce my results, there's no point. Open source, you could say, is really foundational for the sciences. And so within astronomy, we often stand on the shoulder of giants in that there are many people that devote, sometimes even entire careers towards developing these very, very powerful softwares to solve astrophysical problems. A big part of the field is learning how to use those softwares and apply it to the problem in particular that you're very interested in. And sometimes synthesizing many codes together or making your own additions, et cetera, to be able to solve the problems that you're interested in. Having open source is very, very important for that, and being able to be comfortable working with open source software or making your own software open source and publishing that is all, I think, a very key part of, in particular, astrophysics is what we're talking about here, but I think really the sciences as a whole.
What specific software do you use for that?
I use a couple of different softwares. So when we're thinking in the context of just general problem solving, something that you might want is something like a Markov chain Monte Carlo sampler, or something that allows you to sort of input a likelihood function and then minimize that likelihood function. So you might come up with some way to solve a problem. You might say, okay, well, this is my data. So we've looked at our telescopes, we have some set of data. And you might say, okay, well, I want to understand what the cause of this data is. And so to do that, you're going to build a model. You'll say, okay, I think that the underlying astrophysics for what I'm seeing works in this way. So I'm going to build this model. And then you might want to see, okay, now that I have this model, my model is defined by some number of parameters. And maybe those parameters are interesting to us. So in the context of this gravitational lensing, what I'm observing might be the Sunburst Arc, and in particular, maybe the positions or where I see the Sunburst Arc with respect to the rest of the galaxy cluster. I might build some model for the underlying mass, the underlying gravity that's causing that gravitational effect. And so that might be described by some important parameters. A number one being, okay, well, what's the total mass, right? What is the full mass of the galaxy cluster that's lensing the Sunburst Arc? If I want to be able to test that model and solve for those parameters when comparing it to the data, I might need some code that would allow me to do that. And so I might create some sort of likelihood function you can think of. If you remember from maybe high school, the chi-squared test, that's a really great way of doing it. This might be in the form of a large Markov chain Monte Carlo software. So popular ones being something like MC. I think Stan is another popular one. And in particular, like a nested sampler like Multinest. And so that's like a big open source code that I could never hope to write myself, right? Like it would take way too long. It would be way worse than these people that really have dedicated large sections of their careers to developing these. But because it's open source, because it's widely used and well tested by the community, I can feel confident applying those codes to my problems. And then you can go a bit finer, which would be codes that are specifically within astrophysics. Maybe I really want to understand, I'm looking at a star cluster, and that star cluster is surrounded by a nebula, and I'm seeing the light from that nebula. To understand what's truly going on there, you need to do a very intricate calculation of how light from the stars gets transferred through the nebular clouds. It's a very, very complicated physics problem. And there's some 50-year-old now, I think 50-year-old code that's been built up over the course of somebody's career to do this extremely well and extremely powerfully. And that's all completely open source with extremely good documentation, such that I can use it and I can feel confident that it's doing the right thing, rather than having to spend my whole career developing a code to solve a problem I'm interested in. I now get to stand on the shoulder of giants, as I mentioned before, and really use somebody else's code. And that advances my timeline.
Well, Massimo, we are coming up on time. To close out, what advice would you give to aspiring astronomers or those interested in pursuing a career in the field of astrophysics?
Right. So I've got two pieces of advice. Both are conflicting, but I think that there's a happy medium that you can find. So the first, I guess, is for those that are thinking about astronomy, but maybe they really haven't gotten into it yet. I'd say start looking for opportunities. It's never too early to start looking for opportunities to get involved, and you'd be surprised by the number of opportunities that there are. Hopefully, if anybody's listening to this, that they're thinking that they might be interested, but they're not totally sure, I'd say start looking for things. Astrobytes is a great website to start out with if you're looking for opportunities really at the undergraduate level. The second piece of advice I have is really for the very excited aspiring astronomers. So you're already like trying to get into it. You know, you're sending emails to professors. You're already trying to get involved in certain programs or camps or what have you, depending on what age level you are and what level of or where you are in your career. But also understanding that astronomy is it's a marathon. It's not a sprint, right? This is the career, especially if you choose to take the academic route. It's a lifelong career. You have a lot of time, and there's going to be lots of opportunities to sprint. It doesn't need to be all the time. And so definitely like take things easy, enjoy things outside of astronomy, and keep in mind sort of the greater perspective of where your career is going and what the next steps are, really going far off into the future.
Cool. Well, we appreciate you taking the time to answer all our questions today.
Yeah, definitely. This was really, really fun. I always love talking about my research. I think you'll find that any astronomer loves talking about their research.
I think any space lover will love talking about space.
Yeah, definitely. No, thank you for the opportunity to do this.
3, 2,
This has been the System76 transmission log. For more inspiration, check out the website and follow us on social media. On your descent back to Earth, please keep your hands and feet inside the transport beam at all times. Captain Sign-Off, in transmission.